Okay, welcome. Today we're going to talk about section 2.6, which is differentiability. And so the first thing we're going to do is we're going to talk about what it means to be differentiable. And we say that a function is differentiable if the derivative exists at some x value, so whatever x value we're looking at. And remember that this function here, the limit as h approaches 0 of f of x plus h minus f of x all over h, really just means that it's the definition of the derivative. So it really means that we're just finding the derivative there at some x value. Okay, so again, we're differentiable if we can find the derivative at an x value, or at all x values for our function. And if we draw a quick sketch here, what we're also saying is that our graph has a non-vertical tangent line at f. So if we were to draw tangent lines of, say, this function here, okay, um, what we can do is we can draw tangent lines at any points along this graph. And as long as they're not vertical tangent lines, we're going to have a function that's differentiable. And we'll get into a different example here. So this is going to tell us what rules or what cases make our function not differentiable at a certain point. And we have three different conditions. And the first one is that our function is not continuous. So whether that's we have a hole, whether it's a jump somewhere, any type of discontinuity, that means we're also not differentiable at that point. Our second condition is that our graph has a sharp corner, which we also call a cusp. And so if we have that sharp corner in our graph, we can say that that is not a different, or graph, or function, excuse me, is not differentiable at that point. And then the third rule we have is a vertical tangent line in our graph. That will also make it not differentiable at that point. So if we have this graph here, we've got three different points where this is going to be not differentiable. The first one's at B here. If you can see at B, we've got this cusp, we've got our sharp corner. The second point is at D, where we have some sort of jump here, so it's discontinuous. Okay, so a jump, and it's discontinuous. And then at E is our third point. And if you look at E, we have a vertical tangent line there at E. And so that's going to also be our third form of our function not being differentiable. So a vertical tangent. Okay, and so that's just a general function. We're going to look more specifically now at one of our parent functions. And the parent function we're going to look at is the absolute value of x. And more specifically, the absolute value of x when x equals 0. And if we look at this graphically, first of all, we see that, so looking at the graph of this function, we see that specifically at x equals 0, we see that we have this sharp corner we come to, or a cusp here again. And what we want to do is think about what's going on with the slopes at this point here at 0. And if we look at from the left side as our graph is coming in, so our slope from the left is going to end up being -1. And if we look at the slope of the line going from the right side of our absolute value function, or the right side of 0, our slope is +1. And so for a function to be differentiable, we need to make sure that on both sides of our point that we're looking at, whatever that value is, we have the same values. And since we have different values here, this is another way to prove that this is not differentiable at x equals 0. Okay. This next example, we have a piecewise function, and we have to figure out if this is continuous everywhere. That's the first thing they want us to do. And so we have the function g of x equals 2x minus 3 when x is less than or equal to 2, and g of x is equal to x minus 1 when x is greater than 2. So first things first is trying to see if this is continuous everywhere. And when when our function is continuous everywhere, we know that they're going to intersect at that point at 2. So we need to set 2x minus 3 equal to x minus 1, and we're going to evaluate this at x equals 2. So what we can do is we can substitute in then for x, and there was a bell. So we end up with 2 times 2 minus 3 equals 2 minus 1, and we end up getting, when we simplify both these, 1 equals 1. And so this is a true statement, so we say that yes, this function is continuous everywhere. Okay, and now the next step, we're going to try and figure out if this is differentiable everywhere. So what we have to do to figure out if this is differentiable everywhere is we have to make sure, like we saw on that last slide, that the slope coming to the left of negative 2, so the slope of this function, so the slope of the function coming from the left side is the same as the slope of the function coming from the right side. So what I would like you to do is use your definition of the derivative and figure out what the slope is of this function and the slope of this function. So pause your video and give that a shot. Okay, so hopefully you finished and you found that the derivative of g of x when it's 2x minus 3, the derivative of that function is 2. And for our other part of our piecewise function, the x minus 1, the derivative of that is positive 1. And so again, since we have two different slopes, at the same point we're going to say that this is this is not differentiable at x equals 2. Okay, so here we have a continuous function that is not differentiable. And we're going to use this knowledge to make to come up with a little theorem here. And what our theorem says is that if we have our function and we're at a point x equals a, so for that last example we used 2, but for this example, if we're differentiable at any point x equals a, then we can also say it's continuous. So if it is differentiable, then it is continuous. Unfortunately, we can't say the same thing about a continuous function. So continuous does not mean that it's differentiable. It might be, and it might not. We have to go ahead. We have to go ahead and check that. But if it is differentiable, then we know it's also a continuous function. The last thing for this lesson that you have to do is go to this email or this address here. Type this in so you can either pause the video. Let me scroll over so you can see the whole thing. So you can either pause the video and type in that entire email address, or you can go to Google, search the big derivative puzzle, and you should look for this one right here, differentiation 1 math online gallery. And what it's going to do is it's going to take you to an applet that's going to give you some puzzles, and the puzzles are going to look something like this. It's going to be a 3x3 grid, and they're going to give you a few of the functions in there. They're going to have graphs of the functions, and this, excuse me, oops, not F. This is going to be in the top column for each one of these. This is going to be your function, another function, and another function, and you need to fill in the derivatives of each one of those graphs, and then the second derivative. So we're reading each one of these top to bottom. And they'll have separate choices over here for the side on the sides for you to bring in. But try each one of those puzzles, give those a shot. They're a pretty good time. And then when you're finished with that, here's your homework. Thanks.